comes creeping in, illuminates our skin.
What a beautiful day. I'm having such a wonderful walk. What time is it? What? I'm meant to be doing a revision video. Oh, bollocks. What do I do? I'm in the middle of nowhere. There's absolutely nowhere I can get back now. Oh no, this could be the end. I might get the sack.
Oh, Benito.
Yes?
Stop being an idiot. You're not going to get the sack.
Are you sure?
I'm 100% sure of it. You mark my words.
Right. Oh, thank you, what. God, I must say I was getting a bit worried there. So, what is your solution?
Well, don't you edit these videos?
Yes?
Definitely.
Yes.
Well, what are we worried about then, man? You just need to edit this out.
Oh, yes. I don't know what I've been worrying about all series, what? Oh, well, I'll just go back to leisurely place, shall I?
No, get a bloody spurt on, man. Come on.
Okay.
I'm in a foreign state. My thoughts they slip away. My words are leaving me. They caught an aeroplane because I thought of you, just from the thought of you.
Hello everyone. Yes, welcome to another revision video now. We're going to switch things up a bit today. We're going to look at something completely different. Now, those of you on my course will know the next part in evolutionary biology is technically looking at the origin of life. It's basically taking a step back through time and looking at all the things that happened to lead to where we are today, basically. Now, time is running out before the exam, and I feel like I won't get through it all, because there's quite a lot to say. So instead, I'm going to skip that bit, and to be honest with you, it'd be pretty tedious anyway, just be naming a load of key events, just loads of key facts, so it wouldn't really be that great. So, we're going to move straight on to human evolution, which is also pretty interesting. Yes, over the next few videos, we're going to be applying some evolutionary theory to some traits that we see in humans, and start to think about why they happen, and looking at specific experiments which help to explain this. We can't really start looking at human evolution without referring to our closest living relatives, chimpanzees. We share over 98% of our DNA with chimpanzees, so incredibly similar. In fact, we're so similar that if you look in the right places, we're pretty much identical. If you look at blood serum reactions between humans and chimpanzees, it's been shown that we're more closely related to chimpanzees than the horse is to a donkey. Crazy. And the genetic makeup of things such as our hemoglobins are pretty much identical, so we're incredibly similar. But also, if we look in the right places, we're also incredibly different, aren't we? In terms of our demographics, our behaviour, our mentality. You know, chimps can't, make works of art, make big buildings, compose music, all these kind of incredible stuff that humans can do. That's all very good, but humans can also be different to chimpanzees in a negative way as well. Genocide is something which is unique to humans. Also, this stuff about destruction of the environment, the way we're destroying the world's rainforests, which could be leading to the 6th mass extinction, the Anthropocene mass extinction. Probably one of the main things that makes us humans unique is the use of language, which I think we spoke about in an earlier video, is thought to be down to these FOXP2 genes. Another adaptation is this thing called the hyoid bone, which facilitates speech in our jaw. But this hyoid bone also presents some disadvantages because it means that the food pipe and the windpipe can be open at the same time, and this significantly increases our risk of choking. So there must be some pretty big positive selection for us to keep this hyoid bone. Therefore, our ability to use speech and be able to use language is very important for our survival. So we are similar to chimps, but also very different, and these differences are likely to be due to regulatory genes, so genes which control the expression of other genes. The neocortex in the brain has also received a lot of attention lately, in that the biochemical processes within it mean that the neocortex in chimps is very much reduced to that in humans. So this may tell us how we're different from chimps, but evolutionary theory is what tells us why we're different from chimps. And that's what we're going to be going through. We're going to go through a certain number of characteristics unique to humans and apply some evolutionary theory towards them to just show why they exist. And our first case study is all about relatedness and behaviour that we have towards children. Now, our brain is very complex, we know that, and it regulates our behaviour. We also know that it can be acted on by natural selection. So this is what allows our behaviour to evolve, to change over time. But we also know that behaviours differ between different cultures. So that leads to the theory of adoption of behaviour due to your surroundings, and that goes against Darwinian theory. Because of course if natural selection was the only force acting, then we'd expect our behaviour to be the same over a wide range of cultures. We now know that is not the case, and it's thought, due to the environment changing so rapidly, natural selection is having trouble keeping up with the way our behaviours are adapting to new cultures. Now we know that behaviour is a pretty complex thing, right? So we get this thing called genetic determinism, which suggests that our behaviour is only controlled by our genetics. But let's be honest, it's likely to be a really complex mixture of our genetics and our interactions with the environment. And that's what makes us who we are. So perhaps we're genetically predisposed towards certain behaviour, but different cultures allow us to slightly modify and make little tweaks to this behaviour, making us all behave differently. So an example of how human behaviour can have a genetic basis is to do with this relatedness towards offspring. Darwinian theory predicts that the more related you are to a certain offspring, then the more time you're probably going to invest to raise it, to bring it up and increase its chances of survival. So as a result, you're increasing the chance of them successfully reproducing and passing on those genes, your genes, to the next generation. So this is kin selection. Now this isn't just seen in humans, of course, it's seen in lions, and also in primates, where a new father could actually kill the mother's original offspring, and that encourages the female monkey, or whatever it is, to become fertile again. So then they can mate and then raise their own biological offspring. And obviously this idea of the evil step-parent is actually quite common in folklore and fairy tales, for example, like Cinderella, the evil stepsisters. So is there actually any biological evidence for this evil step-parent thing being true? Now, a pair of scientists called Daly and Wilson measured mortality rates in stepchildren compared to biological children. And what they found was actually quite scary. They found that you're 70 times, 70, more likely to die between the ages of 0 and 2 if you're a stepchild compared than if you were a biological child. Now that is a pretty scary statistic, I've got to say. Compare that to the risk of you getting lung cancer if you're a smoker or a non-smoker. You're only 11 times more likely to get lung cancer if you're a smoker than if you're a non-smoker. So, wow, pretty big numbers we're talking about here. But thankfully, this study, the results of this study weren't actually replicated in another study in Sweden. But they did still find that the rate of catastrophic failures is much greater when the child isn't a biological child. Now, another study in Trinidad looked at how a father behaved towards his biological child and his stepchild. So they counted the number of interactions with each child. They also measured the number of agonistic interactions with the child. And what they found was that there was a greater number of interactions between father and biological child than with father and stepchild. They also found there was an increased number of agonistic interactions with the stepchild compared to the biological child. Good grief. What they also found was that if the stepchild was introduced into the family before the stepfather was introduced, there were less agonistic interactions. Now this might be to do with if the child was introduced into the family before the step-parent, then that child is more established in the family than the step-parent is. What was also quite interesting is that there was less agonistic interactions with the stepdad and the child when the mother was around. So there could be some nice, lovey-dovey courtship on beneath all of this as well. A scientist called Flynn then went on to study how the health of step offspring related to family situations, and he did this by measuring concentrations of the hormone cortisol. And this is a hormone, it's a stress hormone, so it's released during stress. And they tested the relationship for the amount of cortisol compared to the amount of days spent off school, and they found a pretty good positive relationship. So we can see here a pretty conclusive positive correlation here between cortisol and days off school. And what the scientists found was, I think you can guess what I'm going to say here, is that there are greater amounts of cortisol in stepchildren compared to biological children. That means stepchildren were more stressed, so that means they spent less days off school. The scientists even took this further to find out that stepchildren had lower reproductive success than biological children. So, what's the point in all these scary statistics? Well, it's showing that our behaviour as humans does have a genetic basis. We have a natural instinct to care more for individuals which we're more genetically related to, because if we spend more time and effort bringing them up, increasing their chances of survival, that increases their reproductive success and allows our genes to be passed on to future generations. So it's all natural instinct. Okay, our next case study is all about fever. Why is the point in fever? Is it an adaptive response for us to try and get rid of the pathogen? So, for example, when we sneeze, is that our attempt to get rid of the pathogen from our system? Or is it an adaptive response of the pathogen? By making us sneeze, it is dispersing the pathogen so it can infect other hosts. Well, we're going to look at a case study which doesn't involve humans. It involves desert iguanas, and they're quite useful because they're ectotherms, so they're cold-blooded. Now, when these iguanas are infected with a pathogen, what they tend to do is to move to an area which is warmer. This increases their body temperature, so this suggests that this fever is an adaptive response of the iguana to try and kill the pathogen. And this has been shown because if you restrict these iguanas from moving, then a much greater proportion of them die as a result. A human study is with chickenpox. Now, a group of humans which had chickenpox were given paracetamol, and another group were given a placebo. And what they found was that the ones that had been given the placebo recovered significantly faster. However, this study shows no evidence that the fever produced as a result of chickenpox is actually an adaptive response. It merely just shows a vague correlation. And also, there was another flaw in this study, that only some of the patients which had chickenpox actually developed fever. So this is a pretty flawed study. However, a much more believable study was shown when studying patients who had the common cold. They were given 4 different treatments. They were given ibuprofen, aspirin, paracetamol, and a placebo. And what they found was that patients without the placebo generally had a stuffier nose, and that there was a greater amount of antiviral antibodies being produced in ones that were given the placebo. So this may not be an immune response. It may just be that the other medicines reduced metabolism of the organism to produce these antiviral antibodies. This idea of fever being an adaptive response has actually been going on for quite a long time. In the 1920s, someone called Julius Wagner-Jauregg won a Nobel Prize for medicine, and what he claimed is that he could treat mental disorders by inducing fever in patients. It didn't work, but he found that he could cure syphilis by introducing a patient with malaria. Now, thankfully, we don't need to do that anymore because some clever bugger invented, well, not invented, but discovered antibiotics. So we're all okay with that now. And this is called pyrotherapy. Now, there are other examples of a pathogen influencing the physiology of their hosts, malaria being a great one. Now, when the malaria parasite has infected you and it's reached the gametocyte stage, that means it's ready to be to infect other hosts. And what has been found is that there's a significantly greater increase in mosquito visitation to the body when the parasite is at the gametocyte stage. So somehow the malaria within the infected individual makes the host more attractive to mosquitoes. So the mosquito will land on the body, suck up the parasite, and take it somewhere else. Amazing stuff. And this is called the host manipulation hypothesis. And it's thought, in this example, to be controlled by odour. So, is fever an adaptive response? Well, we don't really know, really. But it's important that we do know, because that'll significantly influence how medicine is used today. Now, that's it for today. Join me next time where I'll be looking over 2 more case studies on human evolution. But for the moment, goodbye!